Hello everyone, welcome back to ECE410 Power Electronics. This is class number 5. This is a long class, so I'm going to break the video in two parts, part 1 and part 2. So let's start with the part 1. We're going to talk about, first part is switching matrix, second part is switching devices. So let's talk about switching matrix first. So when you convert power from one state to another state, you know that you have to satisfy the KVL and KCL, right? As we discussed in the last classes, KVL, you cannot or should not or must not try to connect two dissimilar switches in parallel, dissimilar voltages in parallel. So you can connect voltage source to the current source or current source to the voltage source, but you cannot connect two voltage source, dissimilar voltage source in parallel. So when you converting the voltage to the current, you have a power electronic device in between to make the conversion happen. So we're not violating KVL because we're converting voltage to current, right? We're not violating any KVL. But if you need to do voltage to voltage conversion, you have to go through an intermediate step like here. So if you go voltage to voltage over here, you have to go through intermediate step. That is, you're going through a current conversion first, then you're converting into the voltage. So these are to make sure that you're not violating any KVL or KCL. So for the switching matrix, we're going to make a matrix based on switching action. So all the switches, we're going to mention them as a Q. When is on, that value is 1. When is off, that value is 0, right? So then we're going to get a mathematical expression out of that switching matrix. Then you can use a software program to develop an algorithm to switch in and out of the switches so that can have a desired output from the input. One of the simplest one is here. I have four switches, right? I have a V in over here and V out over here. Sorry, I out over here. So when I'm doing the switching between them, there are four switches, right? You can have 16 combination, 2 to the power 6, right? So 2 to the power 4. So you have a 16 combination there. But do I need all of them? Think about the one combination here, 1 1 and 1 2 on, 1 1 and 1 2 on. It doesn't do anything, right? It does not connect your input to output. It does not transfer energy. So that connection, that switching action is not useful. And same with if you have 2 1 and 2 2 on, that's also not useful because you're not violating anything, but at the same time you are not producing any useful output. So of that, so what are the not useful one and what are the useful one? Also, you have to make sure that you're not violating KVL or KCL. Think about that. KVL means, as I said, you cannot connect two dissimilar voltage sources in parallel. So that also has another implication over here. Let me draw it over here. They have another implication over here. That let's say you have this, right? Then you have a switch over here and you have nothing over here, right? If you turn on the, let's say V over here, if you turn on the switch, what are you doing? You are connecting this voltage source with a 0 volt source over here. So that's also violation of KVL. So short circuit violates KVL. All right. Now, over here, if you see that there are two obvious combination will violate KVL. That is, if you do 1 1 and 2 1 on at the same time, that will connect your source to a short circuit that is gonna violate your KVL. And same with if you turn on 1 2 and 2 2 on at the same time, that also violates the KVL. And also for KCL, you have to remember that KCL, so KVL, think about short circuit here. And for KCL, you have to think of the current path. KCL needs a current path, right? So while you are violating KVL, you're not violating KCL, because if you turn on 1 1 and 2 1 on, that will give you a good current path for the source. So this is not violating KCL. So for that over here, for KVL not to violate KVL, you want not Q 1 1 plus Q 2 1 on together. So not to violate KVL. And same, you not Q12 plus Q22 on together, right? Then for the KCL, so if you don't do that, if you do that, that means you're not violating KVL. So then for not to violate KCL, not Q, sorry, Q11 plus Q21 off together. So that means to have a current path, you need to turn them on together, right? So this is complete. It's like totally opposite case here. Then not Q12 plus Q22 off together, right? So the opposite case. So one KVL wants you not to turn them on together, and KCL wants you to turn them on together. How do you resolve it? How do you resolve it? To resolve it, that means this is the KVL here. You want them less than equal to 1, and KCL you want them greater than equal to 1. So satisfy both, you have to have them equal to 1. So that means you can have only one on to satisfy both laws. You have to have only one on for that column, right? So Q11 plus Q2 should be 1. So only one on at a time. So if you generalize that, that means you have I is your row. So I and 1 to 2, and Qij is equal to 1. So j could be 1 or 2. If you have more switches in a column, I can go from 1 to n, and Qij equal to 1. J could be any value from 1 to whatever you want. So that means you cannot have more than one switch on the same column, right? So if I expand that to like a little bit more switching over here, so I have the 8 switches over here, right? So to satisfy the KVL, I cannot turn on more than one in one row, right here. So look at here. To satisfy the KVL, I cannot turn more than one there, and also same here, I cannot turn more than one here, right? So that means only one can be on at a time, and there is no KCL restriction, because if you turn more than one, it's gonna give you the current path. So KCL does not care, right? KCL wants one or more on. So now for a particular conversion, we want to have a reference point at the output for the DC. So we can use this as a reference over here. That means I can turn that on and leave it on for the whole conversion. That means, and that column, I cannot turn on any other switches, right? Because you cannot turn on more than one. So if I leave the 4 to on all the time, that means I cannot turn on any of them. So with that, I have only option on the other side, that I have 4 switches to play with, right? So that means your matrix comes like this one is always on. This is your Q42, right? It's always on. This one here, all others should be off, because I cannot have more than one on. Then over here I can play with other 4. So this is the matrix for this particular circuit. So now your software can design the switching algorithm to switch on and off to have a desired output. So let's look at here. So V out is V in times Q. Q is your matrix, right? So V in, you have 4 volts here. VA right here, VB, VC, and this is the reference. This is 0 volts, right? So that's why 0 over here, right? So V out have only 2. This side is 0 volts here, and this side is your V output, right? Because this side is a reference. So now. So that's a V out over here. So V out, if you do this matrix over here, V out is Q11, VA, Q21, and so on, and Q31, and the next one is 0. So you don't have to worry about that, right? Or you can make this big conversion over here, and you see that your 2, 1, 1, 2, where's 1, 2, 1, 2, 2, 2, and 3, 2, this is always 0, and Q2 times 0, because the voltage is 0 there. So that you have only, and also this one is 0, so I have only these 3 here, right? That's basically right here, right? So then V out from this general one, you can V out is first row minus second row and so on. So now this is your input over here. This is your input. Input, and this is switching action over here. So we're switching like the Q11 on for this time over here, and then you have Q21 here, then you have Q31 here, the three switches, right? And then if you see that if when this Q11 on, you have this voltage, this is the part of VA, this is the part of VA, and this is the part of VB, and this is the part of VC. So now your output is this, right? So that's how you can turn on and off the switch for different duration and different time. Then your output will look different. So that's why the software algorithm. Your software algorithm can dictate what kind of output you want and how much you want, how long you want it on. That will dictate your what will be output. So this is your output based on this switching action over here. All right. So in summary, you have V out is Q times V in. If you want the current is the other way around, I in is Q times I out, because your output input power should be same, because V out should be equal to V in. All right. So we have two practice problems here. One is here. I'm going to do them in the class. Then I have another one here. This is the practice problem 2. We can also do it in the class. With the switching actions. Then I'm going to go into the switching device in the next video.